In our first example for friction, we have a car with a mass of 1,730 kilograms that is braking, and it's actually locked its brakes, so it's sliding. We want to know what the friction is between the rubber of the tires and the concrete. As soon as you see that it's sliding, you should automatically think that this is moving or kinetic friction. We'll need to use our formula for friction to calculate friction, and I like to just put a K there when it is kinetic friction. And we'll put the K both by the mu, which is our coefficient of kinetic friction, and for the friction. The mu is basically, I think of it like a stickiness factor. The higher you have of this coefficient of friction, the stickier or the higher the friction between the substances. And it will also depend on the normal force, but it does just depend on the nature of the substances. So if I had rubber on concrete, it's going to have a much higher coefficient of friction, or mu, than, say, rubber on ice. So that's just how sticky the surfaces are that are sliding across each other. Let's also have a look at our normal force. The normal force can be a little bit tricky sometimes, but we'll first start off with the force of gravity. So all objects at the surface of Earth experience a force of gravity down towards the center of the Earth. And if there were no other forces in the vertical direction on this car, it would accelerate or fall towards the center of the Earth. But that can't happen. We know the car's sitting on the pavement or the concrete, and it can't fall into Earth because this concrete is stopping it. And the force that is actually holding it up and stopping it from falling down due to gravity is the normal force. So that's that contact force between two surfaces. It's what stops surfaces from moving through each other, because the atoms don't let of the car don't let the atoms of the concrete move through each other. So there's also this force up because the car is sitting on the concrete. And that is my normal force. It turns out, because these forces are kind of like a tug of war, the force of gravity pulls down, the normal force holds it up. These two forces, if the car is not moving up or moving down, are balanced. It's like no one's winning the tug of war. They're exactly equal, so it's not going to move up or move down like a tug of war would. So we're going to use this. This is a very key fact. Whenever you have something that's sitting on a surface and it's not moving up or down, not accelerating up or down, the normal force will be equal to the force of gravity, or mg. Just in magnitude only. They are different directions, so I'm not going to put the direction on there. And this is only if it is not moving up or down. And I'm just going to change that so it says not accelerating up or down, because that's more accurate. If it's at rest in the vertical direction, then it's not accelerating up or down. And these two forces have to be exactly equal and opposite each other. So they're not, one is winning the tug of war. Once we've got this concept down and our formula, we're ready to actually use the information in the problem to solve for the force of friction. And if this object is moving, say, to the right, so say its speed is to the right, the force of friction is always in the opposite direction to that motion. we'll start by listing what we know. So we always want to do our givens first. And we know that we have a mass of 1730 kilograms. And we know the coefficient of kinetic friction is 0.8. So that's this mu. I'll put the K there as well, and it's 0.8. And one other given that they don't often put in the problem, but we always know, it's that gravitational field strength. And on Earth's surface, it's 9.8 newtons per kilogram down. You might also see it called the acceleration due to gravity, and it might be in meters per second squared, but either works. And then we want to see what we're required to find, and it's the force of friction. So we'll have to analyze our formula, and I'm just going to put an A because I'm running out of room. I want to use the friction formula, but there's a problem. I need to know my normal force before I can use the force of friction formula, because I know this mu sub K, but I don't know my normal force. So I'm going to use this relationship over here, that because the normal force and force of gravity are balanced, the normal force will be equal to the mass times the gravitational field strength. And I have both of those pieces of information right here, so I can easily find that. So my first step, before I can use that force of friction formula, I'm going to sub in my mass from here and the G into this formula. I'm just going to put that this is from the force of gravity. So we do want to just be very careful when we use this, that it's only being used when those two forces are balanced, the vertical forces are balanced. And once I have that, when I plug that into my calculator, I can see that the normal force is 17,000 newtons. And then the force of friction, I can find once I know that, because I will know that coefficient, or mu sub K, and I also know the normal force. So I'll just plug in my 0.8 for mu sub K and my 17,000 for the normal force. And it gives me 17,000 times 0.8 is 14,000 newtons for my force of friction. A few notes here. I took a little shortcut. This is not actually a free body diagram, even though I analyzed the forces. So I just found all my forces here. I should double check there's not an applied force pushing this forward, and there's not. So I can do a quick free body diagram for this. If I was doing the free body diagram, I'll just actually do it over here really quickly. So I can put my free body diagram over here. And I'm going to use a box to show my object. You can also use a point or a dot, but I'll be consistent with what you see in your activities. There is a force of gravity whenever we have an object at Earth's surface. And then because this car is sitting on concrete, there is also a normal force in the upward direction. There's no applied force here, so the car is just sliding. To stop, it was moving forward, and then the friction is going to be in the opposite motion, opposite direction. to its motion. And that's my free body diagram. We should do a therefore statement to finish off, and that is how you solve your friction problem. So you will use that basic method where, as long as the object is sitting on a surface, and usually it is if it's experiencing friction, it's sitting in this course, we'll be doing horizontal surfaces. Then we will assume that the force, the normal force is equal to the force of gravity, and we can use that mg to find our normal force. Sorry, this is quite messy because I'm trying to write quickly. But we would just do a statement or a paraphrase to end. And I can actually put in a direction. So the whole time we're doing friction problems, because we're using just the magnitude, not the direction, I do leave off the direction until the end. And then I can use my free body diagram to say what direction the force of friction is in.